Using Le Chatelier's principle to predict the result of changing temperature. Okay, so we're going to have to remember some thermodynamics from Gen Chem 1. So an exothermic reaction is going to release heat. Remember, that's delta H is less than 0. So a negative value of delta H is exothermic. That's releasing heat. And then an endothermic reaction has to absorb heat in order to occur. So endothermic, we define that as having a delta H that's a positive number, so greater than 0, and that absorbs heat. So using what we remember from Gen Chem, we can then actually add this to our equilibrium. So what I tend to recommend is treating heat like a reactant or product, and then you can kind of treat it like a concentration stress problem. So if a reaction is endothermic, you can add heat as a reactant because your reaction will be absorbing heat. Okay, so it needs the heat to proceed. And if your reaction is an exothermic reaction, it's releasing heat, so you can put heat as a product. So exo, heat is product, and endo, heat is reactant. And that just makes it a little bit easier to kind of organize your thoughts if you've actually written something down on the paper that kind of reminds you. So we've been told this reaction is endothermic. Equally, we could have been given delta H, and the delta H would have been a positive number, so we would know that we have an endothermic reaction. So that means the reaction absorbs heat. So I'm going to write heat on the reactant side of the equation. I can't really fit it in. There we go. All right, so we have a mixture that's come to equilibrium. Predict what change the perturbations in the table will cause. Okay, so the temperature is raised. Okay, so if the temperature is raised, I'm going to interpret this just like I was increasing the concentration of one of the reactants or products. Heat is a reactant for an endothermic reaction. So I've increased the temperature, so I have added more heat. Okay, so just like if I have put more methane in, or more water in this case, I've increased the concentration of one of the reactants. So in order to get back to equilibrium, my reaction is going to shift to the right to favour the formation of products, okay, to use up that extra heat. So the pressure of water, well, water's on the left-hand side, water's on the reactant side, so the pressure of water will decrease because water and methane and heat is being used up in order to make more hydrogen and carbon monoxide. All right, so what about if the temperature is lowered? Sorry. Well, if the temperature is lowered, oh, I went too far there. I'm sorry. If the temperature is lowered, that means we are removing heat. Wherever my thingy's gone, where's my heat? So we are decreasing the amount of heat, which means we're decreasing the amount of reactant that is there, okay? Sorry. So if we're lowering the temperature, we're taking heat out, so we have not enough reactant, right? Because that would be the same as if we took out some methane or we took out some water. We've lowered the amount of reactant that is present. Therefore, my equilibrium is going to have to shift to the left in order to compensate for that. So my equilibrium will be shifting to the left. All right, so the pressure of hydrogen will what? Well, hydrogen is one of my products. So if my equilibrium is shifting to the left, that means more products are being converted to reactants. So my pressure of hydrogen will be decreasing as well. All right, so that would be the approach that I would recommend for an exothermic or endothermic reaction, just treating heat as a reactant or a product, and then increasing or decreasing heat is just like increasing or decreasing the concentration of that reactant or product.